Material is not everything to consider when we're talking about aero components. We must consider design. All right, welcome back. Today we're going to talk about aero components. And more specifically, we're going to talk about material versus design. You hear a lot in the industry, titanium components are best, steel components, aluminum sucks, aluminum will bend. All of these different marketing strategies, really, that companies are using. So let's get down to what matters and why. Some of the common components that are used today are aluminum, steel, and titanium. There's still a couple brass components hanging around, but for the most part, aluminum, steel, and titanium. So let's discuss why one might be better than the other and why maybe it doesn't matter. First, we need to understand what happens when a component fails. For example, if you hit something hard, like this here, right? We've got a bent component there. Not only did it bend the component, but it bent the field tip as well. So that's failure. Notice the carbon didn't fail. It's perfectly fine. But the component itself failed. So let's discuss what makes a good component and what makes a bad component. First, we're going to start with the material. But to do this, we need to understand what our goal is. So our goal is we want a component that's going to be strong, resist bending, number one, resist bending, tight tolerances, concentric with our arrow shaft, which means that when we rotate the arrow shaft, our component rotates exactly the same. We don't have wobble, so we need really tight tolerances between the two. So what material should we use for this? Well, I'm going to show on screen here some of the common materials that I discussed and their yield strength. Now, yield strength is the measure at which the material starts to bend or deform, as it would be known in engineering side. And there's two things to consider with this. There's yielding, which is permanent bending, and there is elastic deformation, is called, or bending, which is where a material will bend, but it'll come back to its natural and original shape. So we're really concerned about bending in the permanent sense, where our insert changes shape. Let's talk about what those stress values are. Strength values, excuse me. And strength is a measurement of stress. So stress, force divided by area. So when we look at these values, we're going to see a lot of overlap. Brass is in the 95 to 124 megapascal range. Aluminum and aluminum alloys, which is most commonly what we use is aluminum alloys, 55 to 700 megapascals. Steel, 2,000 to 1,000 megapascals. Titanium, 170 megapascals to 1,260 megapascals. Now, interestingly enough, carbon, as you might know, as a carbon shaft here, it can bend a lot and return to its original shape. In fact, it doesn't have a yield strength because carbon will bend and bend and bend and bend and bend until it breaks. So it has an ultimate strength, which is significantly higher than that of our components. Carbon doesn't break until 750 to 3,500 is its range. So 750 to 3,500 megapascals. There is two materials, steel and titanium, which do overlap slightly with our carbon arrow ultimate strength. However, generally speaking, we're going to have failure in our component before we have a carbon shaft break. Now that's assuming that we don't split the shaft or perhaps crack it. Our component is most likely going to be our point of failure first over the carbon shaft. We want to design a component that can resist a lot of our stresses in the front of the arrow shaft during impact without bending. So if we want to reduce our chance of bending, what do we need to do? regardless of material, there is the design aspect. I mentioned earlier that stress is a pressure and it's force divided by area. So that means the actual area of our component matters when we're determining what the stress value that component feels. So what that means is the diameter here of the component, and namely this surface area that is facing our impact direction, that matters. So when we compare components from different shaft diameters, so this is a 246, your standard arrow shaft. This is a 204. Those are both steel components. Now, generally we make the outside of the field tip the same, and so the outside diameter of these is usually the same, and the inside diameter will vary. So when we're looking at the strength of these components, here's a prime example of what I was talking about, the inside component. So notice the diameter difference there, quite significant. So if we had two components that are designed exactly the same, then material would matter. And in fact, it would be the primary way in which we would compare those two components, assuming again their geometry has to be identical. If their geometry is not identical, then we can't compare them based on their material purely. Coming back to this yield strength, notice that I gave very large ranges for these materials. And that's because the specific type of aluminum alloy, for example, or the specific type of steel, or the grade of titanium, all matter when we're determining what the yield strength is of that material. So to blanketly say that titanium is better than steel is not necessarily true. In fact, a higher grade steel, let's say it's in 700 megapascals, which is, at the higher end of the 200 to 1000 range I listed. Well, a lower grade titanium might be 300 megapascals. That steel is twice as strong as that titanium in resisting bending. So titanium is not always the best choice of material to use. We need to understand that geometry plays a huge role, and the specific material, the grade of titanium, the aluminum, the exact aluminum alloy composition, the exact composition of steel are critically important when we're comparing these two items. I've found that you quickly find good components and bad components and what they are. So let's have some takeaways that I want to discuss from this video. Material is not everything to consider when we're talking about aero components. We must consider design. We must consider the area that component takes up, specifically from a standpoint of how much force that component can take before bending. The carbon in our arrow shafts are almost always stronger than our components, and that's typically why we see component failure before carbon failure. Now, we do get cracking of a carbon shaft. We do get pressing inserts into the shaft. That's a little bit different mechanism of failure. And again, we can talk about that in a later video. But no, our components are important, but it's the design with the exact material used in those components that dictate whether that's a good component or not. So the next time you're shopping for aero components, consider asking the question, what grade of titanium is this? What is the specific steel used? And what is the specific aluminum or aluminum alloy used? Those are questions that we should be asking as archery community so that we can effectively compare one product to another. As always, I appreciate your time. If you found this video interesting or helpful, please drop a comment and like down below. Consider subscribing to the channel. Reach out, any questions, I'm always happy to chat archery. And this has been the next video for Archery Education. Till next time.